Hi there, welcome back. In the second part of Lesson 7, we consider ARMA models in some little more details. And we will say something about their estimation, we will say how we can, for example, try to understand something more about the autoregressive and the moving average part by looking at the ACF and the PACF. Indeed, in this class we introduce the PACF, that is to say the partial autocorrelogram. After that, we will say something about prediction, so how we can perform prediction with a stationary time series. And we will close our class by introducing a slightly more general class of models called ARIMA. ARIMA models are a generalization of ARMA models in which we introduce a third parameter that is called the integration parameter. In a time series, we know that every observation depends on a certain number of past or future observations, but we'll just consider here the case of past dependence. Okay, so if we are considering the observation of a given phenomenon today, depending on the type of time series, the value of today may depend on the value of yesterday, the day before yesterday, and so on. Okay, and we know that we have different legs if we want in the autoregressive part, if we consider an autoregressive model, in the moving average part, if we consider a moving average model, or in a combination if we consider an ARMA model. Now, we know that a measure of the dependence is the autocorrelation, which is the correlation between our observation and itself in the past or in the future. But again, here we just focus on the past. Now, what happens since there is a time-dependent structure? If I consider the dependence between today and 3 days ago, in reality this dependence is not really clean, because the dependence between today and 3 days ago also takes into consideration what happened in yesterday and 2 days ago. Okay, so if I consider the correlation between my observation today and the observation 3 days ago, I also take into consideration what happened in between. Now, an idea is to try to remove this in-between part. Okay, so to try to remove this intermediate linear dependence that we can observe between today and 3 days ago. In that sense, we introduce the so-called partial autocorrelation, which is the autocorrelation between observation at time t, say today, observation at time t minus 3, 3 days ago, and we remove what happened at time t minus 1 and t minus 2. We will see that the partial autocorrelation combined with the autocorrelation can give us very important insight with respect to a time series. For a time series xt, we define the linear predictor xt hat, which is the object that you see on your screen. Please notice the forward-looking nature of this object. So we are, in a sense, regressing xt against xt plus 1, xt plus 2, and so on, until we consider, for example, a certain number of elements. Now, we take this forward-looking approach because it will also be nice and useful later when we consider, for example, prediction. But you can imagine that if you want, you can also revert, so you can express xt as a linear combination of xt minus 1, xt minus 2, xt minus 3, and so on. But please recall that we are playing with a stationary time series, so in a sense there will be a difference if you want, but it's not substantial. Given the linear predictor, we can define the partial autocorrelation exactly as I told you before, so as the correlation between two different time points once we remove what happens in between. So once we remove the linear dependence in between. So how we do that? You see that clearly on your screen. So we define phi 1, 1 to be just the correlation between xt and xt plus 1, and for what concerns phi h, this is nothing more than the correlation between xt and xt plus h once we remove the corresponding linear predictor. In the Shamway and Stoffer book, you find more details about the manual computation of the partial autocorrelation with some simple example. Now, you can imagine that in reality, when you have a data set and you are analyzing a time series, it is not a matter of first computing the linear predictor and then computing the correlation that you clean via the linear predictor. And any computer software, you have a direct implementation of the PACF. So we will not enter and we will not waste too much time about solving basic exercises for the computation of the autocorrelation. I think there are more important things for us to learn together. As I already told you, the combination of the ACF and the PACF is extremely useful to understand a little bit more the characteristics of a time series that we want to model. Now, in the ACF, what we have, we plot the autocorrelation against the different legs. And for the PACF is the same, we plot the partial autocorrelation against the different legs. By looking at the graphical behavior of these two different plots, we can try to figure out to have an educated guess. Obviously, is not sufficient, you have to go deeper as with all plots. So don't make the mistake of stopping after a plot. As I told you, I like plots a lot. It is probably evident in this course that I like plots a lot, but they are not sufficient. So they are just first steps. Okay, looking at the joint behavior of the ACF and the PACF, we can have educated guesses with respect to the P of an autoregressive model, to the Q of a moving average model, and to the P and Q of an ARMA model. So we can actually try to understand the order of the models that we may want to fit to our data. Now, assume that we start from a time series from which we have already removed the trend, the seasons, the structural breaks. Because what I'm going to tell you in a minute only applies to time series that have been cleaned from the possible sources of non-stationarity. Okay, so we have a time series which is the result of all our detrending, deseasonalizing, and so on. Okay, so this is our remainder time series. This is our time series, and we plot the ACF and the PACF of these time series. That again, I repeat, without trend, without seasons, and so on. So don't make the mistake of reading the ACF and the PACF as I'm telling you now on a time series that have not been detrended. Okay? Now, if you start from a time series and you plot the ACF and the PACF and you observe a long exponential decay for what concerns the ACF, and you observe only a certain number of significant legs in the PACF, and these legs are P, then you are probably playing with an autoregressive process of order P. So I repeat, for an autoregressive process of order P, you can expect an exponential decay in the ACF and only P significant legs in the PACF. Now, when we say exponential decay, remember that we speak in terms of absolute correlation. Okay, so an exponential decay means that you have a long memory in the ACF, but this long memory can be composed of positive and negative legs in terms of autocorrelation. Okay, so you see a long memory in the ACF and just P significant legs in the PACF. On your screen, you see the example for an autoregressive process of order 2. For what concerns moving average processes of order Q, we observe the opposite behavior. So we observe Q significant legs in the ACF and a long memory in the PACF. For what concerns ARMA models, we expect a long memory both in the ACF and the PACF. Then, in order to understand what is the correct P and what is the correct Q, we can have some educated guess by looking at which of the two plots has the longest memory. But we will go into more detail in the applied part of our lesson. For the moment, for us, it is sufficient to stress that in the ACF-PACF graphical comparison, in case of an ARMA model, we see a long memory in both plots. Now let's consider the problem of estimation in autoregressive, moving average, and ARMA processes. Let's consider ARMA processes. Now, if we have an ARMA process PQ, so with P legs in the autoregressive part and Q legs in the moving average part, how many parameters are we supposed to compute? For sure, we have to estimate phi 1, phi p for what concerns the autoregressive part. And we have theta 1, theta q for what concerns the moving average part. Moreover, there is another parameter, which is what is the standard deviation of the white noise that will be what remains after we are able to remove all the information in the time series. So in total, in an ARMA model PQ, we have P plus Q plus 1 parameters to be estimated. In estimating ARMA models, the most reliable approach is maximum likelihood. Why? Because we get a lot of nice asymptotic properties for our estimators. So it's very nice, for example, then to study the confidence interval and so on because of the asymptotic normality that we know comes out of the MLE. So in estimating ARMAs, typically we use MLE. Maximum likelihood, as you can imagine, is implemented in all the basic software you may want to use to fit an ARMA model to your data, for sure in R, as we will do. Even if we do not enter into the details, it is worth saying that just for the autoregressive models, so just for an autoregressive model of order P and not for moving averages or ARMA models, there is another approach. These are the so-called U-Walker equations that for the autoregressive models are quite nice, and they exploit the inherent linearity of autoregressive models. When nonlinearity kicks in, like for example with moving averages and ARMA models because of the moving average part, then it is preferable to use MLE, as we said just a few seconds ago. In estimating ARMAs and in deciding what is the optimal P and the optimal Q, we will have to use some model selection approach. There are many different possibilities. We can use, for example, the Akaike information criterion. That is the quantity you see on your screen and that you probably recall from your courses in statistics. So this quantity is just defined as 2 times k, where k is the number of parameters involved in the model, and remember that in the ARMA model this is p plus q plus 1, where 1 accounts for the standard deviation or the variance, what you prefer, of the white noise, and we have the quantity minus 2 times the logarithm of L, where L is the likelihood of the model that we are considering. Using the Akaike information criterion, we will look for the combination of P and Q that minimizes the criterion. In reality, we will say that it is a little bit more complicated than this, because we don't just look for the value that minimizes the Akaike information criterion, so we don't just look at the values of P and Q that minimize the AIC, but we will also consider a trade-off, because we want to get a model that is parsimonious, that is to say, a model that has, from one side, a good level of understanding and fitting of the phenomenon, but at the same time is simple enough. It is totally silly to fit an ARMA model with P equal to 300 and Q equal to 57, just because this is the value that minimizes the archaic information criterion when we can get a similar archaic, maybe a little bit larger, with an ARMA 3.2. Okay, so as we will see in the applied part, it is always very important to look at the value of the archaic, but also to take into consideration the actual number of parameters, and keep in mind that we want a model that is parsimonious. Once we have estimated the parameters of a time series, the most interesting thing is to make some prediction about the future behavior of the phenomenon under scrutiny. Now, in order to do that, we perform the so-called forecasting. In forecasting, what we try to do is to understand what will be possibly the future average behavior of the phenomenon we are considering. So, if we are playing with a stationary process, we can actually perform our forecast and define the quantity xn plus mn, that is nothing more than the expectation of our process at time n plus m, given that we have observed the process until time n. In other words, we are looking for the best linear predictor, which is the linear predictor that minimizes the mean squared error. From a numerical point of view, this is not a difficult task, and we can easily perform a one-step forecasting. Once we have a one-step forecasting, we can extend to a certain number of steps, like m steps forward. ARMA models can be further generalized. We can, for example, introduce ARIMA models, and after ARIMA models, we can consider SARIMA models, and so on. Now, what is an ARIMA model? An ARIMA model is an ARMA model on differences. So you remember that one of the ways we have considered to deal with the trend was to take differences. Now, if we consider an ARMA model on first differences instead of the original time series, we are defining implicitly an ARIMA model integrated once. If we define differences on the differences, we are playing with an ARIMA model integrated twice. So the integration parameter that defines an ARIMA model and that essentially builds the difference between an ARMA model and an ARIMA model is the parameter that tells us how many times we are taking differences of our data. Now, an ARIMA model is simply defined, as you see on your screen, by using the notation that we have been using until now. An important thing that we have to stress in speaking about ARIMA models is the integration parameter. Okay? Now, if you consider an ARIMA model in which the parameter d that represents the integration part is equal to 1, you're essentially saying that you have a time series and you are taking the first differences. So, in a way, you are detrending or possibly detrending the time series using your differences. Okay? Now, in principle, you can take d equal to 2, so you are taking the differences of the differences, and you can take d equal to 3, taking the differences of the differences of the differences. Now, the more differences you take, the easier it is that you are removing trends and seasons. But it's also true that the more differences you take, it's not difficult to observe that you are losing the actual interpretation of the phenomenon that you are considering. So once you take, for example, 5, 6 times differences of something, what is the quantity? Can you express this quantity in terms of, I don't know, any return, any growth rate? What is the interpretation? What is the physical interpretation of a quantity that has been integrated so many times? Actually, it is very difficult, and most of the times it is not possible. So don't be tempted by the fact that taking a lot of integrations, you can possibly remove a lot of things you don't like in a data set. What is important for us is to keep an understanding of the phenomenon that we want to model. Okay? So what we can say is that typically in finance, D is not larger than 1, and for sure it is not larger than 2. There are fields in which you can have D larger than 2, but is not the case for us. For us, it's typically very, 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 very rare to observe a D larger than 2. And in any case, my suggestion is always to try to fit your trend, fit your season independently, and then rather play with an ARMA model instead of fitting directly an ARIMA model. I will show you in the application that we can actually perform both, so we can first the trend and then fit an ARMA model, or we can directly fit an ARIMA model with D equal to 1. You will get essentially the same result. Yet, from, let's say, an epistemological point of view and also from an interpretation point of view, performing the different steps in sequence is, at least for my personal preference, something better. In many consulting cases, I've seen ARIMA models that were extremely difficult to be interpreted because the integration part, the D, was larger than 2. And what's the point? So you have to find a balance between the fitting but also the interpretability of the model and the usefulness of your model. So you want to be able to use your model for forecast, to make inference. It's not just a fitting exercise, because if you reduce everything to fitting, then you can just fit a polynomial of whatever degree to your data. You will get every single point, and then, okay, good for you. It's totally useless. And we close this part of our lesson by noticing one simple thing. If you consider an ARIMA model in which D is equal to 0, this is nothing more than an ARMA model. So all the models that we are considering, that we have been considering, are just obtainable as special cases of ARIMAs. So if you take an ARIMA model in which D is equal to 0, you have an ARMA. If you take an ARIMA model in which D and Q are equal to 0, you have an autoregressive model. If you have an ARIMA model in which P and D are equal to 0, you have a moving average, and so on. So you understand that in terms of just summary representation, then ARIMA are very efficient, but at the end of the day, what is important is that the model you are fitting makes sense, and that will be our goal in the next steps.